All right, so can everybody see the presentation? I see some thumbs up. All right, cool. All right, I'm going to try to get back the chat real quick because when I opened up screen share, I got rid of the chat and I need to be able to see if you guys are asking questions. Please don't hesitate to interrupt to ask me questions or to say that sounds complicated. If something sounds complicated or is difficult for you to understand, that means that there are 10 other people that it is difficult to understand who aren't speaking up either. And in this case, we don't even have 10 people here, so that means that 100% of everybody else didn't understand that either. So let me go ahead and introduce myself. I think if you've been to Utah Node, then you know me as AJ, the guy who often wears a cowboy hat for no good reason, other than that it looks freaking stylish. And I am a technophobic technologist, which, to clarify what that means, is simply that just because I help build the robots doesn't mean that I don't think they're going to destroy us, because I do. So with that out of the way, a couple of things that I'm doing. One is called Beyond Code Bootcamp. I'm working on writing scripts and creating a video course for people that are either new to programming or just kind of looking to catch some more knowledge to be able to level up their career. So I'll maybe mention that again at the end. And then webinstall.dev is a really, I think this is really cool. A buddy of mine and I have been working on this. So if you wanted to install Node, for instance, on a computer that it doesn't have it already, it is super easy to remember: webinstall.dev/node pipe bash. So we're not actually going to be using much Node today, but if you needed it on your computer, that would get you the latest version. And I've got a bunch of other developer tools that are up there too, and other people are making contributions as well. So if you know of any developer tools that that you think should be easy to install that aren't already, let me know about that. So the presentation is which database to choose: key value, indexed, and SQL. Oh my. So I actually decided we're going to switch the format of this a little bit. I'm going to talk more about data modeling first and then go into the different types of databases. But those are kind of the basic types that you'll hear about a lot: key value, index, SQL. So if you want the short answer of which database to use, there is an answer that's like a one-size-fits-all, and that is Postgres. Postgres is the database that's just got everything in it, but not in a bad way. Not like it's a clunky kitchen sink. Like it's got streamlined pieces for all the different types of data that you'd want to do. And yeah, so it's a good solution. And why is that? You can do NoSQL with Postgres. You can do HStore or JSONB, which are both types of NoSQL. Basically, it's what is similar to what MongoDB uses. You have optional indexes, which is true of all databases, but some people don't know that and they get scared, but you don't have to put indexes on anything. Postgres has a SQL query planner, which basically means that you can ask Postgres. You can say, hey Postgres, here's a query that I'm going to run. Tell me what sucks about it. And then it will come back and it'll be like, this part of the query is going to take this amount of time. This part of the query is going to take this amount of time. Because it looked like you wrote this stupid, I switched these parts around to make it intelligent. And yeah, and so that's really nice. And then it's got like message queues built in with the notify feature and whatnot. So Postgres is just a good all-around database that's easy to explore, lots of different features, and have general knowledge that will benefit you. So I'd recommend to anybody. But what we're going to go over tonight, a lot of it is about knowing the rules so you know when to break them. Because like I was saying before, all databases can be structured in pretty much every way. Like they can all accomplish very similar tasks. And the thing is, you want to know the rules so you know when to break them, because a lot of the confusion about like, oh, well, I'm using this database because X is simply because database Y has a rule that you shouldn't do X. But then it turns out if you break the rule, it can do X just fine. It's just not the way that, it says so in the documentation as the way. So, and then why not MySQL? Just because Oracle mainly. Yeah, Oracle is a big company that just destroys everything it touches. And so you hear a lot about MySQL, but MySQL is kind of dying, and it's because Oracle just destroys all sorts of stuff. So anyway, moving on from that, the too long but read anyway, of course, what answer, what database should you choose? It depends on basically what your data is. And most importantly, this should have its own slide. I didn't put this in there, but like, what question do you want to ask the database? That's what you got to start with. You don't start building a house and then say later, well, how many kids do we want to have? You first think, how many kids are we going to have? And then you build your dream home, And so same thing with choosing a database. You have to think, what are the questions that I'm going to query the database with? And that is not what this slide is about, but this slide is kind of the general two models of data handling, which is the Starbucks style, the asynchronous queue style, and then, or eventually consistent style, and then the Walmart style, like the multi-queue, the sharded style. And I might go into that a little bit later, but basically keep in your mind like the fundamental difference between how these two places work. Like Starbucks has one register, you go up, you place an order, you get a ticket, you sit down, you get called back. The order gets resolved eventually. It's eventually consistent. Walmart, there's lots of different registers. You go to a register, you stand in line, you wait in line, your order is in queue or processing the whole time, and when it's done queuing, processing, the order is done and you leave. There is no it is atomically consistent. One person goes through the checkout, one person has completed an order. So these are different models, and this is a good thing to think about, in terms of your data. Is it important that everything about my data is specifically consistent, and I just need lots and lots and lots of width to handle it all, or is it better, is it just as well that I put things in a queue and that we can resolve any differences eventually? And there's a really, really great PDF from, I think it actually comes from the IEEE, called "Your Coffee Shop Doesn't Use Two-Phase Commit," and it kind of describes this problem in detail. So I highly recommend that you Google that and that you give that a read, because I'm not going to be able to do it justice all on my own, but that's kind of the basis of it. And the model of this, you can think of it like Amazon and American Airlines both are, they use what we would call this eventually consistent model, which is not necessarily the traditional SQL model. But the idea is, if you place an order on Amazon, somebody else places an order on Amazon, and it's Christmas time, and a lot of other people are placing an order on Amazon, and that item disappears, they still take your money. You just get an email a couple days later that says, sorry, we were unable to fill your order, and your money's been refunded. I mean, if you've ordered on Amazon enough times, I can't imagine anybody that's ordered, I don't know. You definitely will get those emails. If you haven't gotten one yet, you will get one where they tell you that something's wrong with the order, and they just fix it. And this is how the real world works. The real world works is when we have problems, we don't anticipate the problem and then try to fix every possible way the problem might occur. Instead, we let the problem happen. We recognize that the problem's there, and then we go fix it manually. And so that's kind of the model. Same thing with the airlines. Airlines overbook flights, and then they just give people, if actually everyone that booked a flight shows up, they just give people vouchers and, hotel stays and free trip to a local theme park or whatever. They just make them happy. So just give that for context. So now let's talk about the data itself and kind of how we model it. So there are a couple different categories of data. Actually, before I go on, are there any questions or comments up to this point? Okay, I'll move on then. So data has different types of relationships, and I kind of put them in three categories. So one is categorical, which is flat data. This is data like what you see, product listings, web pages themselves, like blog articles, things that can be listed 1, 2, 3, 4, 5, 6, and the relationships between them are only tangential. So that's what I call the categorical or flat data. I don't know if everybody else calls it categorical, but I think everybody calls this flat. And then you've got graph type data, which is kind of like the opposite end of the spectrum. It's totally, completely different thing. By the way, the categorical data is super easy to do the Walmart style with. Super easy. Not so easy necessarily to do the Starbucks style, but it's very easy to do atomic on categorical data or flat data. And then on graphs, graphs are like circular data. What I mean by circular is like I'm friends with Dave. Dave is friends with Susan. Susan is friends with Sam. Sam is friends with me. I'm friends with Dave. Dave is friends with Susan's, you know. So if you were to try to lay out all of the data, you can't. It's impossible. You cannot do it because you have these infinite loops where as long as you follow the relationship of the data, you end back where you started from, and you can go in a different direction and still end up back where you started from. So graphs are things like social networks, multi-stop transport routes. Anytime you hear the problem, the traveling salesman, that's this type of data relationship. The data goes in many different ways. And then what I like the best, and I think most things can be broken down into if you give it a little bit of thought, are hierarchies or directed graphs of data. And this is things like, whoops, I didn't mean to click there. Automotive parts, dinner recipes, NPM dependencies. Hopefully you don't have circular references there, although they're technically allowed. But you know, if you think about automotive parts is different from your Amazon shopping, because usually parts are related to one another. If you get, you know, if you want to change your oil, you need to buy oil, but you need to buy an oil filter. You also need to buy this little special washer that goes with where the nut is that keeps the oil plugged. And lots of things like that, where when you buy one product, you actually have to buy like 3 other products to complete the set. Like, you know, dinner recipes, I should have said that instead because everybody gets dinner recipes, you know, but yeah, you know, you need the butter and the salt and the celery and the parsley, you know, whatever NPM dependencies. Hopefully as developers, we kind of understand that a little bit, but that's the idea of a hierarchy or directed graph, is that there's one core concept that then spreads out into sub-concepts or sub-pieces of data, but the graph goes in one direction. We're just looking at it from the perspective of how do I make this dinner recipe? We're not looking at it from the perspective that would be the more graph perspective of like, what are all the ways you could use celery? So that's kind of the general structure. So any questions on that? Because this is kind of it's a really important concept to grasp. This is the most important thing I'm going to say tonight. So any questions on this? All right, we'll look at some data then. Now, when we look at data, we're going to have things like IDs or keys. We're going to have values. We're going to have enums or symbols where the key is a value, and indexes, which are basically like IDs. We'll go into this when we actually look at some stuff. So here I've got some data. Hopefully everybody can read this very clearly. This is super important. So I've called this data.json, and hopefully everybody is familiar with JSON, even if you're a Java developer. I think hopefully you've got some experience with that. And if you're not, whatever, you know, I think this is, if you've done any programming, this should be fairly simple to understand. There's relationship here. So I've got an object, name is AJ, birthday is June 16th, favorite foods are tacos, pizzas, and Mountain Dew. Favorite people are Aggie and Hannah. And then these people have, you know, perhaps their favorite people as well. And so this is a graph structure of data. This is the most difficult data to tackle. And in this case, we're going to say that, you know, for simplicity, you know, ID would really be just a random number. But for simplicity, we're going to say the ID of the objects here is the name. So my ID is AJ, my wife's ID is Aggie, my sister's ID is Hannah, right? And and this could go on forever in terms of those favorite people could have favorite people, and so on and so on and so forth. So if we want to store this in a database, we can't store it in a database like this. We have to serialize it. That means, you know, serialize basically just means it has to be in a format that could be printed on a sheet of paper. You cannot print a recursive graph on a sheet of paper because the paper would reach to the end of the universe and keep going with circular references, as we already said. So if you're part of the old guard, and this is why people get so skittish about SQL. SQL is amazing. It's really the best way to store data, in my opinion. But the problem is that the old guard, they say, well, you have to normalize, that's what they call it, normalize everything, which means that you have to break everything down into flat atomic lists. And so if we were to try to break this down into very flat atomic categories, we'd have one category that is people. And then, we've got name and birthday, which were the only things that were unique to people. So if we go back here, what's unique to a person? Name and birthday are unique. The other things is more of a relationship. It's not part of the identity of the data. So name and birthday here, they're part of the identity of the data. It's not just a relationship. It's like it is the data. Now, if we look at food and people, here I'm breaking apart the relationship that we had before. And it's the convention is that you alphabetically sort with underscores. So food comes first because it's F, then underscore people. And this way data systems it's easier when you're writing programs and object relational mappers and whatnot, if you can rely on some common conventions for how things are named. So that was chosen on purpose, not by accident. And then we've got our people ID, because we don't want to have to deal with like singular and plural and all the different possible cases and things. So we've got our people ID as AJ, and our food ID is tacos. And you can see, well, you can't see on the food side because there actually are no foods that are mutual between the people, but you can see there's duplicate IDs, but there's no duplicate data. So there's a duplicate people ID, there's a duplicate food ID, but we don't have duplicate extraneous data. We've flattened this down. So we wouldn't want to do it where it's people ID, AJ, people birthday, June 16th, people favorite color, blue. We don't want that. We don't want that kind of duplication in the data. And then, down here, favorite people. So this is, we could also call this people. That would be appropriate as well. That would probably be more appropriate in some cases, but for the sake of the example, we're calling this category of data favorite people. And then again, we've got the ID. I guess this probably should have been people ID, but then it would have knocked that off the screen. So I didn't do it that way. But so this is people ID, AJ, favorite ID, Aggie, reason, wife. And so we've created more records of data, but we've eliminated circular references. So we flatten the data. I want to pause and let someone either comment or question about this, because I'm sure this isn't 100% clear. All right, we got a really smart bunch, or a bunch of liars lying in your hearts, telling me silence indicating understanding, but actually having questions you're denying me. We'll see. Okay, so we flattened out the view of the people. So here, this might be what the category of food looks like. Now in this one, I probably should have been more consistent as I was creating this, but in this one we have the ID as it would really look. By the way, in no database should you ever, under any circumstance, use an auto-incrementing ID. You should always use UUIDs. Take note of that, write that down, lock it in your head. UUID good, auto-incrementing ID the devil. And I don't know if we'll have time to get to that, but that's a pro tip, and it will bite you if you do not follow that advice. But here we've got some real IDs and some extra information about the foods. So nothing too special there. I'm just going to move on.
I have a quick question.
Yes.
So by using the UUID on top of the auto-increasing ID, will that have a performance problem?
The problem is in relationships of data, you will get data conflicts when you do like backups and restores of your database, or when you need to shard your database across multiple instances, because eventually one hard drive is not enough for your data. If you're lucky and you develop something where you have a measure of success, eventually a single hard drive is no longer enough for your data. So if you use an auto incrementing ID, you will come up with conflicts that are hard to resolve. And when you go to restructure your application later, it's no easier to use auto incrementing IDs when you're starting your application, and it's much harder to fix them later. So just don't ever use them. And if you're using them right now, just fix that as soon as you can. I don't know if that's, I want to go more into some of the data modeling stuff. If you've got more questions about that particular topic, let's circle back around to it, because that one we can go into more.
Okay, thank you.
All right. Unless by common vote you want me to sidetrack and go into that, by all means, speak up and say, no, AJ, you're wrong. Let's talk more about that. I will listen. Okay. But then this is an example of an enum. So we had our main table where we're breaking apart our people and relationships, and I'm actually showing 3 different categories on the same screen. Then we have just our food, and then we have just our food types. And this is an example of an enum. This is a case where it's okay to not use a UUID as an ID. An enum in a database means the value of the data is equivalent always and forever to the ID of the data. So for example, AJ, I could get a legal name change. I could change my name. It's very rare, but it happens. I can change my social security card. It's very rare, but it happens, right? So I could never use something like that as an ID for myself, because it wouldn't be a good ID. So using a random UUID, and UUID just means random ID. It's like unique, universally unique identifier. Just means random ID, right? Anyway, but if the value of the thing is identical to what the thing means, then it's okay to use it as an enum. And so, breakfast is breakfast. That's what breakfast is. So the ID of breakfast being breakfast, that makes sense. And what this allows us to do is, if I have an enum in a database and I want to, I have this type is breakfast, or this type is anytime, or this type is dinner. I don't want to be able to put in the type, I don't want to be able to put gargle splat into the type field, because that's just random garbage. So if I make an enum table that just has IDs that are what they are for the thing, then I never actually have to query that table or join that query or join that table, but I can have a relationship in that table that basically says, hey, if somebody tries to put something in this field that's an enum field, meaning that only values that are enumerated in this enum table can go in that field, then throw an error. So that's a thing about that. Now with that, we've pretty much gone over what I think are the most important pieces of how you break down data to become a flat structure. Is you break down relationships into pairings that can be duplicates according to IDs. You break down unique information, and you use enums to prevent data corruption. So what this would look like in a spreadsheet, or what you get back from a database, would be something like this. So the one we just looked at, no, the one before. This one, the food one we just looked at, it'd come out of, if we did a SQL query to the database, we'd get something that looks like this. So JSON representation, CSV representation, same thing. Or if we were to look at our enum, if we were to query our enum table, this is what it would look like this. So just different representations for the same data. So this is what we started with over here on the left. And this is what we ended up with over here on the right. We take all the people out, bring them to their own level, da 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 da. I think we explained that enough, but just so you can see them side by side, a second on that. Okay, so the question is, why? Why do we want to make things super flat? And the reason is, for for indexes. So indexes basically just means, I think of it like a phone book, right? Phone book is indexed. It only has one index though, which is last name or business name. You open up a phone book, those of you that are old enough to know what a phone book is. For those of you that aren't old enough to know what a phone book is, I'm sure you've seen one on an episode of Seinfeld. You open it up and it's got last names in there. If you just open it up to a random location and you find a last name, and you know who you're looking for, what their last name is, you know whether to flip left or right. And if you know approximately that you're in the middle of the phone book and you're looking at the O's and you need to find somebody with a last name that starts with J, you know that if you just split it in half again, you're likely to arrive pretty close to the J section. And if you don't, you know whether to go left or right. And then if you split it in half again from that point, you'll end up, almost certainly on the right page or within a page or two. So rather than flipping through hundreds of pages, you only have to make 3, maybe 4 decisions of what pages to look at in order to arrive exactly at the page that you intended to look at. And this is what an index is. In particular, that's a binary search index. But that's the purpose of an index. Now with data, you might want to look up somebody by their name. You might want to index their name so that you can have a book that you can open and just get directly to that. This file on the hard drive, the file is so large, and you can just seek into the file and find its location, right? And then you might want to index more than one thing though. If we're really flat, we just mainly want to index by ID. But when you want to search stuff, you often want to search by more than just its ID. You want to search by something else like name or color or size or whatever. But as long as it's flat, it becomes very, very easy to do these indexes. And even if you have to create kind of like, again, old reference, but there's this thing called the library. And when you go in, they have a book catalog. So if you want to find some information, you don't have to just go to the shelf and start doing your binary search. You can actually first go to the catalog, and there might be multiple catalogs. So you can look in one catalog that's about history, and you can have another catalog that's about art. But yet there's going to be a lot of books on art history that are in both catalogs. This is also representative of what an index is in the database. So you can create these catalog indexes that are not the main data index, but they also allow you to very quickly do your search and then go straight to where you need to go. So you're only a couple hops away. Let's see. And then, yeah, inverted indexes is just, that's binary searches. I was given the example of ID. Inverted index is like when you want to look up by the value instead. So instead of looking up by the ID, I want to look up by the color or the size, like I was saying. Full text search, this is a different type of index entirely. You don't need to have flat data for this. But full text search is basically, you take a book, you split apart every single word on spaces, and then you tokenize all the words that are similar, like, gosh, in English, we have so many irregular verbs. Gosh, just trying to think of a non-irregular verb for a second here. All that, am, be, ran, all of those are irregular, but shop, shopped, shop, shopping, you tokenize it, you just get the root word as shop and you insert that into an index. So that's what full text ends up being. Okay, so now to other ways that you could look at this data. You could look at this data, instead of doing it flat, you could kind of do semi-flat. So you could have the data be favorite people. We have a limited set of favorite people. Like I only have maybe 10 favorite people. I don't have 100 favorite people. So if I were to, instead of saying I need to follow the rules of the old guard and break down everything flat so I can index everything, if I just think, well, what questions do I need to ask the database? I'd say, well, it might be really common when I get a user profile. I don't need to get all their 500 friends, but I might want to get their 5 best friends. I might want to actually store that data with the person so that every time I get their profile, I pull it back up. You know, same things, favorite foods, like how many things have I liked? 10,000 things. We don't want to put that in the user profile. That needs to be sectioned out categorically and put in flat storage. But my favorite foods, or like my favorite things, my most favorite things, it's a bounded set. It's limited. It cannot grow beyond, you know, 10 or some number, but it, you know, it's very small. So when you find that you have things that are very small, it turns out that you can break the rules. You don't have to flatten everything out perfectly flat. So you can have, and this is what, you know, Mongo built their whole business around, was basically the idea of let's break SQL rules. Let's say that you don't have to flatten things if they're small. And so it's very common in a Mongo database that you will just leave some things nested, and sometimes they'll become inconsistent. Sometimes you'll have a fight with your favorite friend and you'll remove them from your friends list. And there might be some period in time between when they get removed from your friends list and when they later get removed from your favorite people list. But this is, you know, inconsequential in the grand scheme of things. So it's okay to have like some bad duplicate data for a limited amount of time until the errors, you know, when your profile gets pulled and it tries to reference a friend and it finds the friend isn't there. So it's like, oh, I need to go update this data and remove it from here as well, or whatever. You have these situations and it's okay that the data is out of date for a little while. So the problem with doing it this way, data can become out of date or inconsistent. The benefit of doing it this way, you don't have to have lots of indexes or lots of lookups. It becomes very simple for someone to look at the data and understand it. This is a little bit easier to understand than this is. So anyway, that's one of the rules that we can break. So now I rearranged the data part of the slides because I thought that would be the most important thing to talk about first. So now we're going to go back into the types of databases now that we understand the types of models of data. And I'm going to go through the types of databases and try to pair what style of data modeling fits to that style of database. So before I do that, any questions up to this point? Okay, moving on then. So the first database I want to talk about is the oldest database, and that is a key value store. And this is typically for flat data, but it's actually what the early SQL databases were built on top of, just multiple key value stores. So things that, that you know of that are key value stores, things that whether or not you know it, you use almost every single day, every person uses almost every single day, are things like the file system. Every time you save a file on your computer, on your phone, ultimately it ends up on the file system. And typically the ID is the path. So /users/AJ/pictures/image_5672.jpg. That is the key. What is the value? The value is the image that's in the file. Berkeley DB is one of those old Unix databases. It's an embedded database. And this is what MySQL was built on for like the first 5 versions or so. Maybe it's just the first 4 versions. Anyway, Berkeley DB is a binary key value store. This is very similar. Basically, Google created something similar to Berkeley DB called Level DB. So every time you're using your web browser, anytime the web browser needs to store some piece of application data, it gets stored in Level DB under the hood. And it's just a key value store. It has, I don't think it has the ability to do indexes. I could be wrong, it might. But it has the ability to zip compress data to make it smaller. So it's like it's like their broccoli compression or some, I don't remember what the compression is, but I think it's like Google's custom compression algorithm that's more efficient for some things, I guess for browsers. CouchDB is a document database. It's not as popular as it once was, but it's the data sorts going in rather than the data sorting coming out. But at the core, it's key value. Local storage is what local storage uses LevelDB under the hood, at least in Chrome. And this is also called blob storage, binary large object, often, because the way that these key value stores often are used is, I give you a key and it's just a string of bytes. It doesn't matter what it is. And then I give you a value, and it could be a picture, it could be a PDF, it could be plain text, it could be HTML, it doesn't matter what it is. So these are, when people talk about blobs, what they mean is just arbitrary data that's often of a nondescript type. We don't care until we get it out. So that's key value, typically used for flat data. Oh, and I should have showed the pictures. So here we are. There's your file system storage. Then we've got document databases. And what these are for typically are things that only get written once and that are pre-indexed. So some examples of that would be semi-structured documents. By semi-structured, I mean completely unstructured is just arbitrary text. Semi-structured is like a web page. There are links. The links have meaning. They are typically representative of something in the paragraph that is relevant to the paragraph, but it kind of takes a human to use their brain to figure out why it's relevant, or Google's machine learning algorithms. But you know, a computer can't innately understand. So HTML is a semi-structured document. Hugo builds web pages. It's a very popular static site generator. So Hugo is a program, but it kind of functions in a way as a document database, because it creates a document database. You put Markdown or HTML files in, and you get a web page out, and the data that you get out is more structured than what you put in, because it links it together and creates a nav bar and creates a listing of articles. And when you click on an article, it has tags, and you can click on a tag to get a listing of tags. But everything is done beforehand when you put the data in. Wikipedia is kind of similar to this, but some of the indexing on Wikipedia, at this point, I imagine it's all being done when you click save, but there might still be some of it that's done when you actually view the page. There's a database called MarkLogic that's like this, and then JSON and CouchDB. CouchDB I also mentioned is, you know, you can use it as a key value store. But CouchDB, you put in JSON like that user object I was showing earlier, and you have some rules. And basically you say, when I save a person, go look up their favorite people by ID and then include their top 5 favorite people in this as well. And these rules you write in JavaScript. So they're not rules that you put in a language of the database. They're rules that every single time you save a new item to CouchDB, it goes over the document of JSON and it runs the rules on the document, and the rules tell it what index should it be stored in, if any, and what pre-processing should be done on the data. Do I want to turn dates from integer values into string values? Do I want to concatenate the first name and the last name together as a display name? So all the optimization for how something is going to be given back to whatever consumes the data, that you know, the query optimization is done as the data goes in, not as the data comes out. These types of semi-structured document databases are not good for arbitrary queries. They're only good for queries that can be predefined. So a good example of this is audiobooks. Audiobooks are, when you import your audiobook, there's actually a little bit more data about it. You know, it's got an author, it's part of a book, it's got a sequence number for each track. So there is some semi-structured data about an audiobook, but you're never going to change it, and you don't re-index audiobooks. Like I'm never going to query an audiobook like, give me all of the tracks read by Michael Dene, right? That's never going to happen. That's not ever something that's important as someone who's using an audiobook application. So the only data we care about is put all of these things in the right order, because I'm never going to shuffle them, and make sure that, you know, that I can see by author, because sometimes I might be in a Dale Carnegie mood or a Dale Carnegie kick, or I might remember a book was by Dale Carnegie. But the indexing, the structuring is fairly light. So then we've got relational databases. And these are general purpose, really good databases for just about everything. There's a couple cases where they fail, but typically, SQL databases are relational databases. These are databases where you want to read a lot of things and you want to write a lot of things. General purpose. You can structure them with indexes so that they're favoring reads or so that they're favoring writes. But yeah, that's their general purpose. So, and they operate on the sum of the parts. So everything generally in relational databases, you want to get things as flat as you can. That's not to say that you don't break the rules. So we go back to here I'm breaking the rules. This is good. We want to do this in relational databases when it's necessary. The reason that we want to do that, the reason we want to break rules in relational databases is because the more rules you have in a relational database, the slower the writes will be. Typically, the more rules you have, the faster the reads are and the slower the writes are. And so if we have data that doesn't change very frequently, also the other thing about structured databases, relational databases, is that the more structures you have, the more lookups have to happen. Now with a database like Postgres, it'll analyze your query and it'll say, okay, you want a bunch of stuff from this table and a bunch of stuff from this table. These tables are small enough, I can just start preloading some of this. These tables are really large, so I should index on this instead of doing what you told me to do, which would be dumb. So Postgres is a bit smarter about this stuff than most databases, or at least it can be with the right settings. But the more relationships you have, the more work it has to do. I mean, think of it like, the library catalog. If I have to go look in the history catalog, and then I have to go look in the art catalog, and then I have to go look in the food catalog. If I have to look in all these 3 catalogs, all of that is time that I'm not spending at the shelf getting my book. And so that's where people have the biggest complaint with relational databases, is you end up digging into, you create lots of catalogs because you flatten data, create a catalog, flatten data, create a catalog, flatten data, create a catalog. But then when you go to say, okay, I want to look up information about how to create this great chicken Alfredo dinner, well, it has to go look up the measuring catalog, and it has to go look up the meats catalog, and it has to go look up the vegetables catalog, and it has to look in all the different catalogs, and that can make the reads slow if you do too much of it, and it can just make things annoying to work with. It can feel bad. But anyway, Postgres, MongoDB. Now MongoDB, the funny thing here is MongoDB is absolutely a relational structured database. Now people talk about it as if it's not. If you use it like a document database, you absolutely can. If you use it like a document database, you're going to have a hard time. You have to think, they say, oh, well, you don't really have to think about the schema of the Mongo database, meaning the shape of the data. When we call it the shape of the data, because literally it's, what does the shape of the data look like? Like if you model the data, what shape observes? And you might look at that on graph form, or you might look at it in a JSON form, or in a spreadsheet form, but whatever way you want to consider it, you're looking at this general shape of how things connect and whatnot. So in Mongo, you do have to be aware of your schemas, but Mongo's indexes are a bit looser than something like SQL or SQL databases in general. And so you can put off some of that stuff and worry about it later, but I would say that the trade-off is about the same. It's like, do you want the headache now? Do you want the headache later? Do you want to get it right the first time? Do you want to get it right the 10th time? Like whether you're going with something like Postgres or you're going with something like Mongo, you still end up having to answering the same questions. Don't let the marketing guys trick you. They're both good. They both do a lot of the same things. Postgres is a little better for some things. Mongo is a little better for some things, but they're similar. IndexedDB is what we get in the browser. I believe this is also built on top of LevelDB, but then lots of APIs. And IndexedDB is not like any other database I've ever used. It gives you raw ability to index. You can create a SQL database out of IndexedDB. I don't know anybody who's used IndexedDB on purpose with their bare hands, personally. I probably do, but I don't remember what the use case is. So when you hear about that one, I don't really know what it's that great for, but the web SQL polyfills are built on IndexedDB. Then you got SQLite. SQLite and Postgres are both super advanced in terms of databases. The core difference is that SQLite is what applications on your phone use when you're offline, and Postgres is typically what you use for client-server relationships. Your Skype chat history is stored in a SQLite database. Your like probably think I haven't actually specifically looked at like Discord and Slack, but these are the types of things that use SQLite. They're things that are installed in a desktop environment that don't have to be online connected, but you want them to work offline and to have pretty much the same data and have the data still be searchable and usable. So SQLite is one of my favorite databases because it just gives you the power of everything. And of course you can put JSON in there as well. And then Facebook's Cassandra is, it's like a big data database. And I don't think Facebook claims ownership of it anymore. I think they kind of handed it off to Apache, if I remember correctly. But Cassandra is similar to a SQL database. It's just meant to be bigger, and so some of the constraints are relaxed. So Cassandra might be kind of like a halfway point between Postgres and Mongo. And most of the stuff that we're going to build day to day, it's not necessarily the right solution for. But if you have, if you're getting to the point where you've got hundreds of millions of records, everything else on this list is going to fall off except for Cassandra. And I'm sure someone is going to argue for both Mongo and Postgres, because the zealots are always going to argue that their database can solve every problem. But realistically, when you get into the hundreds of millions of records, you start to tend towards these customized enterprise databases and less of these like general class type databases. And Cassandra is kind of in a middle range where it's supposed to be fun and familiar for people that are familiar in the Postgres Mongo world, but be able to function with the billions of records scale. And then structured data, a good example of an application would be music. I do want to search music by artist. I do want to search music by album. I do want to search music by title. And I don't need all of the results omnipresent all the time. It's okay if it takes a second to find something. But generally, this is a bad example because the iTunes app does not work nearly. I don't know how they make it so slow. If you asked me to sort 1 million items in a database, it would not take as long as it takes to find 10,000 items out of their music store. But I think that's because they integrate with like Siri and like other stuff that slows it down. So it's not doing direct queries anymore. But the general concept is iTunes is a good example of a structured relational database where there's many things that you want to query off of. And then another type of database we have is the append-only log. And this is particularly useful for many read, many write type scenarios. And in fact, most databases implement append-only log under the hood, regardless of what type of database they are, or they have an append-only option. And I did talk about Redis in here. I should have talked about Redis probably with key value stores. Redis is, no, it's like semi-structured. It's a little bit better than a key value store, but I don't know why I didn't have that on here. Anyway, Redis follows the append-only log format. And what happens with these is basically, say I have me, this is what Facebook is going to do. If I go to update my profile, Facebook is not going to go into its index catalog and find me, pull me off the shelf, open me up, print out new pages for my profile, stick it in, put me back on the shelf. That's not what Facebook is going to do. What Facebook is going to do is Facebook is going to create a new book for AJ with all the new information. It's going to save a copy of it right then and there, and it's going to put it in the quickest place that it can put it, and then it's just going to make a little update to the catalog of people. And it's going to cross out my old book number, my old Dewey Decimal number on my book, and it's going to write in the Dewey Decimal number of my new book. And this is the basic concept of an append-only log, is that you never delete data, you never update data, regardless of the database might have a command like update or set. But under the hood, it never touches the old data. The old data is there forever, never, 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 because it's cheaper just to keep the old data than it is to try to go, potentially change the size of the data and need to move other books on the bookshelf, if you will, to make room for it. It's cheaper to just write a new book, put it in the first spot that's available, and then jot down the new ID number of the new book in the catalog of where all the things are. And this, and most SQLite works this way, well, to some degree. Most databases work this way, if not 100% to some degree. SQLite, Postgres, most of your databases work this way. And they have a command that's something like vacuum or garbage collect or clean. And so every once in a blue moon, when you don't have any users on your database, you run the vacuum command. And what it does is it goes through the entire library of data, category by category, and it rewrites the entire, it makes new copies, rewrites the entire catalog of data, and then places it in a new shelf, and then it bulldozes the old shelf. And then it does the next thing for the next shelf, and it just goes shelf by shelf, and it rewrites all the data. And that will drastically reduce your database size. And so depending on what your database is and what your use case is, if you have lots of writes, eventually you'll need to learn about whatever that database calls its vacuum command, because you'll want to run it to free up that space. And yeah, this makes reads a lot faster too, because all the recent stuff that's recently changed, which is likely to be recently read, is all up there at the front. And when the database does its indexing, it makes heavy use of these catalogs. And then when it needs to read the data from start to finish, it just skips everything that's marked as deleted, basically. I mean, I guess you could think of it like it goes over and puts a piece of red tape on the book that's not used anymore, kind of thing. Okay, and so a good example of an append-only log is if you go to myactivity.google.com, you can see a nice unstructured or semi-structured rather view of everything that you have ever done in Chrome on pretty much all of your devices. So this is actually also really helpful if you want to remember something that you were looking at that you forgot. And this is beyond your browser history. This is like actually stored on Google. So you clear your browser history, does not clear your Google activity. But yeah, that's a good example of an append-only log. Another one, of course, the classic example is just your Unix logs, your web server logs. You know, we don't think of these as databases, but they are. If you work with any of these enterprise tools that query logs, like CloudWatch is something that you're likely to run into. At some point, you'll work with a company that uses Amazon CloudWatch, or if not that, then Splunk, or if not that, then a similar tool that's in that category of tool. Then it literally reads every single line and then just does a full text index search on it. And you can go query your logs and say, hey, did this IP address ever try to come after us? Or let's look at the logs for this particular time. And be able, and you know, see that what happened on that day because something was deleted that wasn't supposed to, or whatever. You know, we need to do an audit or something. So your actual real system logs are a good example of an append-only database. Very unstructured, but very append-only. Writes and writes and writes and writes. Eventually, when it hits a certain size or a certain number of hours or days, it compresses the log into a zip file. It saves a copy of it, and then it starts a new log from scratch. And so you'll have gigabytes upon gigabytes of logs that only take up megabytes of space because 90% of the information is the same thing over and over again. Similar IP addresses, similar dates, similar user agent strings, whatever. So it compresses very well. Oh, and one other thing that we needed to copy, there might be one, or cover, there might be one more after this, but message queues. Message queues are not a database per se. They're generally ephemeral. Ephemeral is just a fancy word to mean temporary, or I'll give you a good example of ephemeral. Like, I want to keep this remote control around for a little bit, so I'm going to put it right here in the top of the trash can and save it for later. But then when the trash gets taken out and it disappears, I don't care, except I would care if I did that with a remote. But the general concept is something that's ephemeral basically means you put it in a trash can so that you can get to it quickly right at the top of the trash can, and then eventually the trash can gets emptied out. So you hear about ephemeral databases, ephemeral virtual machines, ephemeral tables. That's what ephemeral means. So my message queues are typically ephemeral. I just put something at the top of the queue, and eventually it's going to get thrown away, and I don't care, but it makes it easy to access right then and there. And typically your message queues are write once, read once, meaning that you put a message in the queue, like, I want to order pizza. This is a message queue. Or the Starbucks example, this is a message queue. I'm going to put something in there. I'm going to write it once. It's going to get read once. It's going to get thrown away. And in some cases, you want it to be read multiple times. So instead of saying, once this is read, delete it, you say, once this has been around for 10 minutes, delete it, because it might be that multiple people are going to log on to Twitter, and so multiple people are going to see an update that was just published by a particular popular Twitterer. But then after 10 minutes, once they've had their glory, if there aren't enough favorites and likes, then it just goes into the trash can. And typically the same thing. Message queues are usually a copy of data that is, not the permanent copy. It's a copy of data just for recency purposes, just so it can be around. And so Postgres has a message queue. AWS SQS is a good example of a message queue. RabbitMQ, basically anything that has MQ, any buzzword with an MQ in its name is a message queue. And then event stores. These are all types of message queues. And let's see. Oh yeah, so good example of a message queue. Get notifications on your phone. The notification itself is actually stored in a database, probably a SQLite database or Apple's core storage database on your phone, but a copy, one-time copy of that message gets pushed to your notifications, and as soon as it's looked at or interacted with, it's deleted. That's message queue. Oh, and then I think this is the last one that we're going to go over is the full text search. We kind of already talked about that a little bit, but full text search is just it's completely unstructured data, just like key value store, except instead of in a key value store, you say, we're going to ignore all of the data. We don't care about anything except for the key and that there is a value. We don't care about knowing what the value is. Full text is data that is unstructured, but you just index everything about it along certain metrics or guidelines. And so Postgres has a full text search. SQLite 3 has a full text search. AWS Elasticsearch, Apache Solr, also called Lucene, or maybe it's built on Lucene, and Sphinx. These are all full text indexes. And a good example of this would be something like Amazon. Again, it's similar to the model that we described with CouchDB, where you get a new product, you get a new data set or document, you put it in, and you process the document once. When we're talking about CouchDB, we run some rules on it, and the rules are specific. They're not generic. Full text search databases, you're making it as generic as possible. So rules for a full text search database might be how close certain words are together, or might be how many times a word appears on a page. That kind of stuff might be kept. Whoops, why is this? Oh, that's not. Because this isn't a web page. I can't scroll it. It's a picture of a web page. And by the way, if you have not tried Miracleberry, I highly recommend it. If you've never done a tasting party, really cool. These little babies make lemon taste like candy. So it's hard to imagine. It's totally legal. There's nothing fishy going on here. It's just a little protein that's in the berry, and it causes your tongue to freak out and make everything taste like sugar. So I didn't pick this on accident. I wanted to tell you how awesome Miracleberry is if you've never tried it. But this is a good example of the full text searches. And this actually does have some semi-structured data as well, with the brand, the item, form, flavor, whatever. But when you do a search on Amazon, it's just looking for things that match keywords, and it doesn't know which words are going to be the keywords. The person uploads an entire description, and what it may do is it's going to follow some rules like this for the full text. It's going to say, if there's multiple fields typically when you upload full text. The title is going to say get a +5. So for every word that I search, if it matches the title, give it +5. And so all these catalogs, like we talked about earlier, everything is a catalog. Every word has its catalogs. And then every catalog is tagged with, where does this word appear as a title? Where does this word appear in the description or the abstract? Where does this word appear in the complete body of the text, anywhere in the body of the text? And so all of that information might be tagged. And then you've got, that when you do the search, it'll say, okay, for title matches, give it +5. For short description matches, give it +2. And for any match at all, give it +1. And so you do your search, and if you have 4 words are in the title and 1 word is in the description, of a particular match, that's obviously going to be very high. And then other matches, it's something that it only matches in the body of the description but doesn't match in the title is going to rank a lot lower. And you typically, text search databases, you tweak the settings on them. So, you turn the dials, you say, well, titles are super important for my use case. And descriptions are actually just complete marketing garbage. So we don't want to pay attention to those at all. And we're going to split the text into a top third, middle third, and bottom third. And the middle third is the words in the middle third should be rated the highest. So that's kind of a weird example. That's not, maybe that's not a real example, but that's kind of gives you a picture of the idea of how full text search is, that you give things certain weights based on certain criteria. And in the case of SQLite, which is where I've used full text the most, you actually recompile the code with the weights. So in SQLite, you actually write a C function to do your weighting, and then it gives you a bunch of parameters, and you just write the bare code yourself of if it's in the title field, I'm going to multiply by 5. Some of the other databases are a little bit more user-friendly in terms of someone who's on the business end and not on the developer end can tweak those dials. And if you think about it, like there's a lot of companies that are kind of doing more or less full text search for company data. I kind of hesitate to say it, but like maybe something like Domo or Tableau, you could kind of think of in that way. I guess that's more semi-structured data than full text. But anyway, that's that. Oh, no, there's one more. There's always one more. Graph. We've already talked about this like a lot, so I don't know that we really need to talk about it that much. But there's Neptune, there's ArongoDB. I've not used either of these. There's another one I forget the name of. But these databases, as far as I'm aware, graph databases are typically really tightly integrated into the language, because the way that full graph object storage databases, the way that they work is they store the data as pointer references. So when you rehydrate the data or deserialize the data out of the database and back into program objects, the memory references match up and stuff. So these are not very common. They're very niche as far as I know. I think actually this one, ArongoDB, I think is not like what I just described. I think it is more like a Cassandra style type of thing. But yeah, again, we talked about graph data. And then one thing I needed to mention, GraphQL is not a database. A lot of people think that GraphQL is a database because it gets talked about with databases a lot. It is not a database. It really doesn't have any, all GraphQL does is stitch things together. It's more of a protocol. GraphQL is more similar to email than it is to a database. Like email gets sent from one database to another database, and I get a nice interface where I can click on it. And the way that the email gets sent between different databases over the internet is standardized. So I have a standard common format that any email from any email service provider can go to any other email service provider, and they both understand the handshake. GraphQL is kind of a way to take different databases and mix them together with a common handshake. I got graph database and object store mixed up, I think. Neo4j is the object store database where it actually is keeping like memory references that it's serializing and deserializing or rehydrating. And that's the thing I know the least about, so I'm not going to talk about it. Data warehouses, I don't know that much about personally, but they're called column-oriented databases. And they're like the opposite of what we talked about with flat data. Well, they're equal but opposite. So a data warehouse is like where, I'll give you a real example. They're used often in machine learning. And a good example is a convenience store wants to find out how to sell better, make more sales on Fridays. And so they take every customer record with every single item in the store. So if there's 10,000 items in the store, or SKUs, SKU meaning the little sticker on the, that's SKU is the sticker on the product that has the barcode. So when you work with product companies, SKU is a word that gets thrown around all the time to mean a product. Anyway, So for all the SKUs, there's a column in the database. So if there's 10,000 SKUs, there's 10,000 columns in the database. Basically, it's a giant spreadsheet. And then they take every order. If they've had 6 million orders in the last day and they want to analyze Fridays, so they're going to take 6 million times every Friday. So they're going to take, 600 million records for the past 2 years, and they're going to compare them with 10,000 columns each. And they're going to run it with a machine learning algorithm, which is just a fancy way of saying putting textbook statistical algorithms in code. Like machine learning, well, machine learning can be a lot more than that, because you've got neural networks on the other side, which is like the sci-fi side of machine learning and the artificial intelligence learning robots type thing. But we're talking about data warehouse. We're talking about machine learning in a very simple college textbook statistical sense, known algorithms that everybody knows about. And you're just running through tons and tons of data and doing lots and lots of comparisons over and over and over again, doing statistical analysis, and then letting the statistical analysis fold and say, well, from all the data I've computed so far, this looks significant. So now I'm going to narrow it down and I'm going to rerun everything, focusing only on what's significant. And then, okay, this emerged as significant. So I'm going to fold it down and I'm going to rerun everything, only focusing on this. And it might be multiple statistical models that run over and over again. But at the end of the day, the convenience store comes out finding out that on Fridays, diapers and beer get bought together very frequently. And then they have to ask the human question, why in the world are diapers and beer being bought frequently on Fridays? Well, because it's the end of the week. Wife wants a night off as well. She asks the husband to go pick up some diapers. While he's picking up diapers, he picks up beer. And so the convenience store then uses this data to say, okay, let's put diapers and beer closer together. Can't have it too close together because the ladies will freak out, but we'll put the diapers on this side of the aisle and we'll put the beer on the other side of the aisle. So you don't see them at the same time, but they're right next to each other. And then we'll increase our beer sales and our diaper sales, because then when they come in to get beer, they'll also get diapers. And this is like a real world thing that actually happened with a real store. And that's what data warehouses are used for. Get the hugest set of data possible and just crunch numbers on it all day long. I should have brought this up while I was talking about it, but yeah, just giant spreadsheets. Time series, oh, there's always one more. Time series is similar to flat data, but you're just looking at it in prospects of time, like you specifically time is something that you want to be able to do queries on and graph and find relationships between. Geospatial, and again, like time series is kind of a feature that might exist in many different databases. I don't know particularly off the top of my head, like a database that operates in time series mode. It's more like algorithms that you apply to data. Geospatial, so if you've ever played Pokemon Go or heard of Pokemon Go, Pokemon Go is a geospatial database developed by the NSA through a company called, I forget their name. But they also did that other one, the other one that I'm showing on the screen, which I forget the name of. These are geospatial databases. It's fencing. I want to know where something is in relation to something else. Geospatial databases are used for like inventory tracking and shipment containers, geofencing for like, is an employee on site? Are they where they say they are? House arrest, flight data. Like, these are the types of things that go into geospatial databases, and they just make it easier to index on points that exist in three-dimensional space. And then you got, your custom databases, which, there's Google. Google's such a freaking weird database. You ask what's the weather, it searches through its app store of available Google apps, which are widget store, whatever. Like, I don't know where all these are, but you just search something and a widget pops up. You've got this little micro app that suddenly appeared in your browser. Yeah. And then you've got a lot of these results are going to be similar to full text in the sense that, if it has weather in the title, it's going to rate higher. So if you're writing your blog posts on Google, it actually does make sense to write the blog post as the title of a question that somebody's going to ask, perhaps the very question that you Googled when you were trying to find the answer for it. But anyway, nobody knows what goes on at Google. They have a lecture series, which I highly recommend if you're into computer science, that you check out. It's called, I think it's Google Tech Talk MapReduce. and I'll see if I can find that and put that in the chat. But this is like a 3-hour total lecture series that goes on how Google makes their database work. But we don't know. You know, we get the general gist of it, but and the custom databases, of course, you're building yourself. Like you're building for a very specific application that is either so specific that you don't want a competitor to have access to the intellectual property of the database, or that just no one else would care because it's just such a niche use case. Yeah, so that's that. So that concludes my presentation on the databases. And now I will ask again for questions, and we're free to meander in any direction. And I'm going to put this up on the screen in case you're interested. I'm working on shorter, conciser videos on specific topics. So this was very, you know, free form, but with Beyond Code Bootcamp, what I'm working on is more scripted material where it doesn't drag on quite as long. But so if you're interested in that, as I come out with that, feel free to sign up there. But other questions about databases, indexes, when to use what, why. We could even talk about specific database syntax, because I didn't put that up on here, unfortunately. Okay, what happens inside the data lake? Was that autocorrective database? I don't know what that question means. Like S3? So S3 is a key value store. S3 I would not consider to be a database. I mean, it is, because everything that holds data is a database. But S3 is a literal key value store where the key, and that's even what they call it in their API, like there's slashes in S3, and S3, you know, you can put a slash in a name, but the slash is actually part of a name. There's no such thing as a folder in S3. There are buckets, and buckets contain keys which have values. So when you look up something from S3, if you do a search, a prefix search in S3, it's actually scanning all of the keys, because S3 is not indexed by folders with slashes. It is only key and value. It is intended that when you access S3, you know exactly what you're trying to get out of it at the moment that you access it. It is not really intended to be searched as such. You just get a list of all the keys, or you pick a specific key. But I actually was not familiar with the term data lake. Delta Lake. I'm also not familiar with Delta Lake. All right, well, if there are no more questions, then we're free to shoot the breeze for a couple minutes. I want to be out of here in the next 10 minutes. So by 7:30, I want to shut this down. But yeah, I'm done. I'm out. Peace. Over. Presented. You're welcome. Ian says thank you. You are welcome also.
Okay.
You're welcome.
See ya.
All right. Adios.
Nice
Do you have any feedback for me on that presentation?
Oh, nice one. Hey.
Was the content valuable for you?
Yes.
Okay.
Thank you. See you.
All right. Bye.
Bye.
All right. Well, we're out.